Right. Okay. So credits, we were giving credits to those fantastic people. And so just click on these links later on if you want to know more, particularly the model description, I think is very well done by Fedor here. And you can click on this and it'll take you to his course where it is all very well described. Okay, so we'll just take a shortcut and we'll just quickly look at basically what is the main equation of the model. So it's a very synthetic model, which is kind of amazing. So these three equations here give you all you need from this model. So let's quickly look at it. The first line here describes what we called the expected value function. So EV, you remember we cast this problem in expected value function space, so not in usual value function space, but in this space where we can have a closed form representation of the expectation with respect to the extreme value shock. So you remember this looks like this. There's a log over the sum of the two options. So this is option 0, and this is option 1. And you do exponential of the value of this option plus exponential of the value of that option. And that is, so this red line here is the expected value over epsilon, which would be the extreme value shock of these future value functions. Okay, value of option I at a shock epsilon I. Okay, something like this. So that's the red line. And so you see, that's very convenient because you don't have to do any integration or any computation. It's just a straightforward analytical form. Then we have to integrate the x part here is with respect to the law of motion of the other state variables, which in this case is the odometer, so the mileage transition. You remember there was this thing where the miles move up probabilistically. So the bus does not, we don't actually track actual, we don't model the behavior to drive the bus a lot or not. That would be too complicated. So we just let the bus move up certain bins in this mileage grid randomly. And so there's going to be a probability with which you can move up 0 bins, 1 bin, 2 bin. And I hope you remember that. I think that would be good to look at just quickly. So let me just quickly open this notebook here. This is a rendered version. You can quickly look at this. The one thing you need to remember is this bit here. Okay, so this transition matrix is really key. So, and it looks the same for replacing or not. So here it's D0, which would be not replacing. If you don't replace and you're in state number 1, so this is state number 1, with a certain probability, you stay in the same mileage bin, so it discretizes the continuous space of mileages into bins. So in the first example, we'll have 90 bins. So here you can move up, you don't move up, you stay in the same bin, you move up 1 bin, you move up 2 bins. Okay, so he really simplifies it like that. There's no way you can move up 4 bins. And that's it. So that's an important object that you should remember. No. Okay, here we were. What did you do? Oh my God. All right. So the second part here, the little v is called the conditional value function. So it's a value function conditional on discrete choice D. Okay, so we'll have the utility function conditional on discrete choice D. And here's the future part, which is this function here. By the way, this way of writing it, the T star means that this is the Bellman operator. So T is the Bellman operator. And you see this is the definition. So we have this equivalent sign here. So we just write down what the model needs to satisfy in equilibrium. Okay, so that's just the definition of the model at equilibrium. An implication of this solved model is the last equation, P of D, which is just the conditional choice probability, so the probability of choosing a certain discrete choice D. And again, thanks to this assumption on the extreme value shocks, on the shocks being extreme value distributed, this is going to have this very simple form, so the simple logit representation. Okay, and that's it. So we will need those objects in order to estimate the model. Okay, so let's look now how exactly we could do this and what's going to happen. Okay, final thing to keep in mind and kind of very important is that this object here, so we will compute this object, and then we will confront this object with what we see in the data, right? So this P function. And you need to realize that the P function depends on what this function looks like, because we will use this line to compute that line. And so the parameters that we put into this model, like the U here, will have certain parameters, which we index with theta. It's very small here, hard to see. So U will have parameters in it, which we call theta, behavioral parameters, deep parameters. Of course, for each different theta, you will get a different U. For each different U, you get a different V. For each different V, you get a different EV. For each different EV, you get different of those guys. And so the whole thing is going to depend on the structural parameters. Okay, so that's going to be the key problem. And so we'll try to deal with that. If there's any questions, just ask at any point in time. Yeah, exactly. So that's also something that hopefully is not too confusing. I wrote it with a pi here. So the transition law for mileage state, I wrote it as a pi. When in the paper, this is a subset of all the thetas. So you just call all parameters theta. And the last ones are kind of the pi. Okay, so we'll just take care not to get confused here. The pi is a subset of the theta vector. Okay, so here's this main function, which we'll have to compute, the likelihood function. So let's just look at it. So we'll write it like this, calligraphic L as a function of this parameter vector theta, and EV as a function of that theta. And in our case, it will look like this. We will have 162 buses in our application today. Each bus will run for TI periods. So we have different amounts of observations for each bus. We'll have to take care of that. And then we'll just construct the likelihood in the following way. So the likelihood of the data, which remember was data in this setup is two vectors. One vector that gives you the mileage state, and one vector that gives you whether or not bus was replaced. Okay, and so we will deal with that by having a probability of replacing the bus at each mileage state, x. So that's the first part. And we will have a probability of moving up certain number of bins in x. That's the second part. Okay, so we'll have to compute this thing. That's what I said. P is the result of the structural model, and the last part is an exogenous transition law. Okay, next thing we do, we take the log of this likelihood because it has much better numerical properties and it's easier to work with in general. So you see it becomes a sum now instead of a product. But that's it, just taking the log of the above expression. Then estimation. What is estimation of this model? Well, estimation, like in many settings, can just be cast as an optimization problem. So we just want to solve the following optimization problem. We want to make this log likelihood function as big as possible. Okay, so we want to choose our model, means choosing theta, so that whatever is produced by the model, this P thing here, is as close as it gets to what we observe in the data. Okay, you know this very well. That's just what it is. Keep in mind that this is an unconstrained problem. You can see there's no constraint attached here. Okay, and in terms of implementation, we will again focus on the average log likelihood, and so we will divide the output of this function by n, just again to improve the numerical properties of this optimization problem. Okay, then how could we do it? So we said there's two strategies that we look at today. There's more strategies, but we will look at two. And the one we'll start with is the classical one, and it's called nested fixed point, or short NFXP. That's the original one, the one proposed by Rust in his article. And okay, so in the first box above where it says credits, I already hinted at the caveat that what I'm showing here is kind of the naive version of what John Rust did. So if you want a sophisticated version, you need to look at his paper, or even better, he has a manual online which describes in extreme detail the algorithm And then you can see how exactly he did it. So I can point you towards the things that he did much more sophisticated than what we do here. But let's go step by step. Okay, so NFXP, nested fixed point, is a double loop. We looked at this last week. We basically have an outer loop where we choose theta. Then given theta, we have to solve the model. So we have to find this fixed point here. We have to iterate on this thing, make EV such that it is the same as the operator applied to EV. And that's it. So that's the inner loop. So we have two loops. And so let's just build it. Okay, it's a bit of plumbing, but that's part of the job. So let's just do it. Okay, let's go slow, but let's do it. What do we need? So what do we need to build? All right, so we need a log likelihood function that is going to give us L, like here. So we want this, something that gives us back this number. Then we want a nested log likelihood, which is going to take a candidate theta. It's going to build a data type Harold for us. So just some structure that stores the relevant data, computes the model for this structure, and gives it to the function in point 1 to evaluate the likelihood at this particular model. And the final thing, the kind of most encapsulated thing, is a function that we can give a name, like NFXP, for example, is going to be a function that does everything. Loads the data, sets a starting value, calls the optimizer, and is going to call the nested log likelihood function. Okay, so that's going to be the cookbook for getting this off the ground in the first instance. Okay, so just quick to remember, how do we solve the model? I just showed you before. There's this separate notebook, which is the one I just showed here, which reminds you how we did solve the model. Okay, so the model solution is a basic value function iteration, like here, and we just needed to have these components. Okay, we needed a data type. We called it Harold. I already referred to it. We need a Bellman operator that does the T thing on EV. We need something that iterates on that relationship, and we need a function to compute the replacement probability. Okay, very simple. All of these functions are in the function library of this notebook, at the bottom of this notebook. Okay, so you can go there and look up. I literally copy and pasted from that notebook into this one. There's the same stuff. Okay, so when I'm going to say value function iteration, you can just remember what we did in this previous notebook right here. Okay, last 2 weeks ago. Okay, so let's not waste any time here. It's pretty standard. So maybe let's just look at Harold. Okay, so maybe that's a good repetition. Where's Harold? Here's Harold. So just to make sure we remember what Harold looks like. So Harold, if you don't remember, Harold was the first name of Mr. Zurcher, who was the kind of the main actor in Rath's model. Harold Zurcher was the bus superintendent of the Wisconsin bus company. And so we called it Harold. Harold chooses N, which is the number of bins in which he wants to discretize mileage. He will choose a maximum amount of miles to consider. RC is the replacement cost, kind of this main big cost that he incurs when he has to replace an engine, which is a big job, supposedly. C is a number that is going to be the slope on the operating cost function. So even if he does not replace an engine, he has to service the bus. And that presumably will increase with the amounts of miles that the bus has run. So there's kind of a slope. Okay, so more miles, more cost. Then there's a vector theta, which are the transition probabilities of the mileage state, these exogenous probabilities, staying in the same bin, moving up 1, 2, 3. Beta is the discount factor, some numerical settings of when tolerance is reached and when convergence is reached. And then there's a state space, very simple. There's just one dimension, just mileage. So what's your mileage state? And there's a transition matrix. And then we have this constructor which builds Harold for us at some default values. Okay, these are just the values taken from John Rust's table for a particular setting of the model. Okay, so that's what we did last week, and please go back there if you don't remember. Okay, so here we are. We load a bunch of packages. Won't comment on those. That's just what we need here. And then let's set up the likelihood function. Okay. So we'll do that in a particular kind of way. We'll set it up so that we can, at will, estimate pi or not. So it will leave us the flexibility to specify pi, this, the transition on the mileage bins exogenously, or we can do it within the full estimation. So we'll call those two things partial likelihood and full maximum likelihood. Okay, and so we just want to write it like this. So okay, what is the likelihood going to do? So it's going to, for a certain solution of the model, so we compute, so we have theta in hand, we compute the solution of the model, which gives us a decision rule in P, and then we'll have an array of data which tells us what the model predicts that Zurcher will do at each observed mileage state. Okay, so in the data, we have observed mileage states, bus traveled 100 miles, 50 miles, etc., etc. For each of those values, we want to ask the model, well, what are you going to do with that mileage state? You're going to replace or not? Or no, we're going to, with which probability will replace? Okay, that's the key thing. We'll ask him, what's the probability? And we'll put that in a vector P model, P underscore model. And then we'll put that next to what Zurcher actually did. Zurcher replaced or not. So that's going to be in replaced data. And we want to confront those two vectors. Okay, let's see how we could do this. So here's the function, called it log likelihood. It's going to take Harold. It's going to take this array from generated by the model. It says probability model. Here's the replace data, true or false. It's a bit array generated by Harold. There's the data on mileage state, and there's the increased data. How much slots did they move up? Okay, and then we'll choose whether we want to do the theta estimation or not. So whether we want to do partial or full maximum likelihood. That's the last thing. Okay, first thing we'll do, we'll look at how long these data are. So number of periods, NT, length of the replacement data. We looked at those are the same length, all of these data arrays that we give in. And then we compute the probability of replacing. Okay, so the probability to replace is this array generated by the model. And we index that array at the observed mileage states. Okay, so this comes from the model, is an array that tells you at which state, what's the probability. And here we collect what are the states in the data actually. That's going to give us this vector. The complement of that vector, of course, is the probability to keep. So that's 1 minus that. And that's what we need for the first part of the likelihood function. So we call that log L, log likelihood. We take a log of the probability to keep times the probability that he did not replace, that Zurcher did not replace, plus the probability that he did replace times the observed replacement choices of Zurcher. Okay, so that's how we will compute the first part of the log likelihood. That's the part that relates to big P. Then, if we do the mileage transition, so if we set this to true, we have to also add on our estimates of these mileage transitions. All right, so how do we do this? So here we create a vector P miles, the probability of miles moving up. We just grab those from Harold. Harold has it stored inside it. So it's the component theta. And you can see that I generate here, I add whatever I have in Harold, and to make sure I add a last element to it, which makes sure this sums to 1. So I do 1 minus the sum of whatever Harold has in it, just to make sure that the solver doesn't do any stupid stuff. So the nonlinear solver will choose these numbers for me. Okay, and so in general, it's very hard to, I mean, it's not, it's not straightforward to restrict this choice. We said it's an unconstrained optimization problem, so we don't want to put any constraints on this at this moment. Okay, so we have to be this is a little hack to make sure that these probabilities indeed sum to 1. Okay, so we can obviously set bounds. So we'll say to the solver, choose these thetas between 0 and 1, each of them. but you can obviously see that does not guarantee that they will sum to 1. Okay, so if I don't want to mess around with any nonlinear constraints here, I can just kind of try to hack this like that and say, I'm going to force this to sum to 1, and the clamp will mechanically bin everything into 0 and 1. Okay, so this is very brute force kind of way. This is kind of trying to force the solver to make sure that these thetas are valid probabilities. Okay, in nonlinear optimization, you often have to do these kind of tricks and hacks and try to guide the solver into a certain direction. And then once you computed that, we can just add it to the log likelihood function, the first part here. You remember it was just a plus, so we do log of this mileage transition at the increased data. So what do we see in the data? How do buses move up certain slots? And then we just compute the corresponding probability from that. Okay, so all of this assumes a certain structure of the data, which I did not show you. So what does this look like? What do all these data arrays look like? It's in the library, the way we built this data function. We don't have enough time to look at it, but just look at it. It's just a certain way to do that. Well, I hope you're still there, because the video just closed now, but I think all of you turned off the video. So let me know if you're no longer there. I'm sure how you would do that, but anyway, I'll just keep talking.
Still here.
Okay, great. So, and then we output. So the output of this is just going to be -1 and the mean of that. So we say we want to return the mean. Okay, so you can see here, this is a very simple. So here's the first part where this is naive with respect to Rust, because we only compute the function value. We do not compute the gradient of this thing, right? You remember, if you want to do a good performance in optimization, you should always supply the gradient, which we don't do here. You look at Rust's data or at Bertel's code, you can see that they do this, and that of course makes a big difference. Okay, we don't do it because it's kind of cumbersome, and you need some sophisticated math, I would say. Okay, but still you can do it. Okay, then we do the nested log likelihood function. So that, remember, is going to take theta and give it to the model to solve it, and then compute the likelihood on that solution. Okay, so here is what it does. X is going to be the vector given to us by the nonlinear solver. H is Harold. D is the data frame of data that we prepared with a function further down below. We'll look at some data output just now. Okay, the first thing we do in this nested log likelihood function is we update Harold. Okay? Harold is created somewhere. Given what the solver chooses to do at this state, we need to update Harold. In particular, we'll take the convention that the first element of what the solver does is the replacement cost, and the second element is this slope on the operating cost. If we chose to also estimate the transition probabilities, so if the length of this vector is greater than 2, well, we'll stick those into Harold as well. Okay, so we'll say that these thetas are whatever the solver considered there, and we rebuild the transition matrix. Okay, so remember we have this function transition, which makes the transition matrix given a certain choice of transition probabilities and a certain choice of bins. Okay, with that we have an updated Harold at that point, so we can give it to the function that computes the solution to the model. So in our case, that would just VFI, value function iteration, and that spits us back a solution, a vector of values representing the value function, and a number of iterations just to check how long that takes. And then we give the solution vector to a function that we call CCP, which would compute the conditional choice probabilities. Okay, that's just a very simple function. And it gives us back PR, which would be the probability to replace at each state. That PR is the thing we give to the log likelihood function. Okay, so let's just quickly about. We call that replace array. Okay, so that's the array that tells us the probability to replace at each state. Right, that's here. It's this guy. And what else? So we have, well, so to the likelihood function we give, so these are all parts of this data frame, which I'm not going to show you, but it's just, Why not? I'll give it a short to you. I guess it's here. It's not defined. What did I call it? It's further down. We'll look at it, okay? So don't worry, we'll look at it. It's later, it's further down, so no problem. Let's just finish this setup. And yeah, so basically the switch, whether we want to do full or partial maximum likelihood is just determined by the length of x. So if I choose x greater than 2, that means that I do full maximum likelihood, okay? So that's just a simple switch here. Okay, then that's it. So now we can put it all together and write this NFXP function. NFXP, that's right. All right, so how can we do it? Well, so we give a couple of keyword arguments to just set some whatever default values, which we then, so we build a default herald, which has some unrealistic values in it, you see, so just to start him out somewhere. Then we get the data. Okay, so the function is bus data, so that's the one we'll look at just later down. Bus data is a function of herald because it depends on how many grid points herald wants to consider. And so then this function bus data will discretize the data according to the wishes of herald. Then we get some initial transition probabilities. If we want to do full maximum likelihood, we estimate those with a simple binning estimator. There's another function down there, which is called partial MLE, which will just, it's basically a histogram of how many times do you observe certain, steps, and then we'll just count, and that will be the first estimate of those transition probabilities. Pretty straightforward. And we add those to the starting value. So we create a starting value vector x naught. Okay, so replacement cost, C, and the vector of transition probabilities on the mileage state. If we don't do that, we do partial MLE, we just have 2 numbers to estimate. Okay, replacement cost and C, operating cost. You see, just 2 numbers. And then we give this x naught. So x naught tells us what method we will use in a sense, because if it's only too long, we do partial maximum likelihood. Okay, so we give it to our function nested likelihood above. We just define that above. Remember, this is how we write an anonymous function. Okay? And so we give this anonymous function to the optimizer in order to create what we call a closure. You may remember, because the optimizer only wants to choose one thing. He only wants to choose x here. But our function depends not only on x, it also depends on herald, which I call here z, and on the data frame d. So an easy way to pass these things together in a package to the solver is this way, to create a closure, an anonymous function in this case, and just write it here. Because like this, we will kind of package this function call up such that z is always going to be this z, and d is always going to be this d within the function call. Okay, then of course we have the starting value. We choose an algorithm with which to optimize this here, which is BFGS, and some options maybe. So I said show the trace only if we say don't be silent. And then we have to choose a certain output. So if we did full maximum likelihood, we have to output all of our estimates. Otherwise, we output only 2 estimates. Okay, so that's it. That's a big thing. That's how you do, in general, nested fixed point. You have a function that loads the data, optimizes. The thing you optimize is something that takes your parameter guess, computes the model, and gives you back some notion of how close this is to the data, and you keep going on this. Okay, so I said close to the data. That's on purpose, because of course you could also do something like a GMM or simulated method of moments, or there's many ways you could do this. You don't have to do maximum likelihood. In this instance, it's a maximum likelihood operation, but you can also do other, I like to call those interfaces to the data. So you can just check how close the model is to the data, and you keep iterating on this. Okay, so look at the data. That's what I promised. So let's just quickly look what this data looks like. Here's the partial MLE function, by the way. So this is just this binning estimator that we will use to get an estimate of these transition probabilities. Well, so is there much to say? Well, we just count how many entries we have in each bin of increases. So dx1 is the increase in mileage state x. So we normalize that such it gives a probability, and we forget about the smallest category just because it's too small. Then what does it look like? So here we have the average replacement indicator mileage states by bus group. Okay, that's kind of a long title. Remember in the paper there's 4 bus groups, 1, 2, 3, 4, and they're of different basically makes, different brands, and that matters because you can see, for example, here that's the number of buses on the y-axis, and that's the mileage state on the x-axis. You can see that only certain buses reach a very high mileage state. So, for example, only group 4 goes up to mileage state 40 in this instance. So what is this doing? This is n. So this discretizes the data into different bins. So let's just look at 90. That's going to be the default. So if we put this into 90 bins, that's kind of the data that we'll deal with. Okay, so all the bus groups factor like this. Only bus group number 4 has is ever going to reach the highest mileage states. The others don't. And so this will, this should inform our, also our interpretation of the results. So it's only the bus group 4 that reaches the very high states. So if in our value function we see that only the very high states we replace, that has some implications for how we interpret the results. Share replaced. So this tells you how many buses of that group did you replace at a certain state. Okay, so you can see the data is quite coarse. So there's not many replacements going on. BD, right, here's this thing. That's the bus data that we create from Herald. So this is what the data frame that we use in estimation looks like. There's an ID for the bus. X is the mileage state. Okay, so it starts in bin 2, then 3, and 5. You see, so we moved up 2 slots here. Again, 2 slots, etc. The bus type, so this is group number 1, and this is dx1, telling you how many slots does x move up from here to there. So it's going to move up 1, 1, here moved up 2, 2, 2, 1, 1, and so on and so forth. And so in this partial MLE function up there, we use this vector here to just count how often does each number occur. Okay, because that's basically this simple estimate of how the mileage state does transition. And of course, the very important column here is D, which means what's a discrete choice? How often do you replace? And so for all of those, it's false. Sometimes it's going to be true. And so that's really what we plot here. Okay, here we plot the share of true given a certain mileage state. Okay. So I actually had a full homework on this to work with this data. I think it's still somewhere actually. Yeah, look at that. So it's here. It's homework 6. So if you want to know more about this, so this is exactly the way I built this data set, and starting from the raw data in a CSV file. It's kind of cool. So if you're interested in how they do this, have a look at this, and then I can give you some solutions later on. So of course all that stuff is missing, but it's nice to, maybe it's a nice way to get started working with the data frames package. Okay, so that's a little homework. If you're interested in how we built this data, how we end up with this data frame here, then you could look at that. Okay, good. Right, so I think it's time to run this now. And so let's do it. So here we see one of the main tables of the Rust paper, table 9, which has these structural estimates for the cost function and the replacement cost. fixed point dimension 90, so that means he used 90 grid points in this particular table, and here is going to be the estimate. So we will focus on this column because it uses all the groups 1, 2, 3, 4. So we will focus on this column, trying to get close to this column. Important number here is the discount factor that he chooses. So it's very close to 1, and then he does another version with 0. Just tries to compare those two results and test whether that's a reasonable assumption that it's 0 with a myopia test. And so let's see. So our focus is going to be whether we can get very close to these numbers here. Okay. All right, let's see what we can do. So we run the function at the default values. Default values, what were they? They were here. So we do a 175 mileage grid and 0.9. So 0.9 is much smaller than what he does. All right, so let's see. So if you run it at this, but that's the wrong mileage grid. So wait a second. Should have set it to 90, right? The default value. So let me just quickly change that. Okay, obviously I want to compare this to 90 because I will show you this table that doesn't. Oh, right, here's 90. Okay, that's just the default run. Okay, let's forget about this. Here we choose it with 90. So 90 bins and a reasonably high beta. So what do we get? We get 9.15 on the replacement cost. That's 9.75, so not quite there. And the slope here is 3.7. That's 2.6 here. So it's a bit too high. But we do kind of partial maximum likelihood. Okay, so we fed in these numbers here. We gave these numbers to the algorithm. You can see when we choose two numbers. Okay, so I would say fairly close, those estimates. And as expected, they're not there because we're missing a 9 here, missing a last digit. We're missing this last digit because it takes forever to run the way I did it on my computer. Okay, you remember that if you make this beta very high, the time it takes for each value function iteration just becomes painfully long. Okay, very, very long because the convergence is so slow. And that's the main bottleneck of this way I did it, of this naive nested fixed point way. Here's a second main improvement that Russ does on this thing. He has a very, very smart way to do this value function iteration. He calls this a Newton-Kantorovich iteration. So what he does is he has a very peculiar way to, well, I'm not sure, it's the first time I see it, that's why I call it peculiar. He does these iterations in two different ways. So first, there's a way that does a very, very big steps, very fast. I think that's a Kantorovich thing, or is the other way around. And it relies on being able to compute the first derivative of the operator. Okay, it's called a Fréchet derivative. So it's a very peculiar thing, but he's able to compute that, and therefore he can do this much faster. Okay, so doing 0.999 for us is not a problem. It goes extremely fast. If you do it in a naive way, it becomes a problem. You can't actually do it. Okay, so what do we get if we do yeah, so I see. So here, okay, I'm just trying to remember what I did. So here we do partial maximum likelihood, but I did not set the right values. I think that's what's going on. Yeah, so here I set here I do full maximum likelihood. If you do full maximum likelihood, you get much closer, you see? So you get 0.97. That's pretty good. You get 0.62. All right, that's really good. And you get the transition probabilities almost totally right. Okay, so that works well. If you do full maximum likelihood, even with a beta that is not as close as one as his, you get, let's say, the right estimates. Okay, let's just call that the correct estimates. I think that's reasonably fair to say. Okay, good. So that's a big success already, and clap ourselves on the tap ourselves on the shoulder. We made it this far, so that's already quite good. And that's it. Okay, so you can see there's two ways to do this: partial and full maximum likelihood. And so the method seems to recover the estimates of the original paper. Now, the main purpose of this lecture, in fact, was not to show you that, but was to show you how to do this with MPEG, with another method. All right, so we're making progress. So let's see. In MPEG, we approach the problem differently. You will remember. So the problem was to view this as a constrained optimization problem. And so we will take the likelihood function as the objective function, as it's written here. The main insight is that now you have two sets of choice variables. So not only theta as a nested fixed point, but also EV. Okay, so that's kind of weird. You kind of need to wrap your head around that, I think. Then you choose the model. So you choose EV in this approach. The solver chooses EV. The solver decides what the model should look like. Okay, this is kind of weird to think about the first time you think about it. But in terms of a mathematical problem, there's nothing unusual about this. There's just two sets of choice variables. The objective function depends on both. And there's a constraint attached to this problem. Okay? That's fine. We know how to deal with this. We know how to do equality constraints, etc. There's methods for that. This is a nonlinear constraint because, of course, t here is an extremely complicated function. So it's a nonlinear function, etc. But that doesn't matter. Right? That's fine. We know nonlinear constraints. That's fine. We can do this. And so that's kind of the idea of MPEGs. There's very good nonlinear solvers out there, which can handle a large number of choice variables. So we can have theta of a reasonable dimension. We can have EV of a very big dimension. And we will still be able to compute that. Okay. Of course, there's limits. You know, if you have a billion choice variables, it's probably not going to fit in your memory and so on. But that's fine. Okay, so let's just build this thing. So the way we'll do this, we'll imagine a JuMP model that we built somewhere. We call it M, and we'll add components to it as we go along. Okay. Again, we want to be able to do full or partial maximum likelihood as before. And we use the same data that we built, the same data frame. We'll say big N is the number of mileage states, and big J is the number of bins that the state can go up at most. Okay. Okay, first thing, add variables. Okay, so of course we have to now add choice variables to the JuMP model. Right, remember what those are. They are of two kinds. They are, first of all, the structural parameters, the thetas, and they are the model itself. All right, so here we come in. We have add vars. It will take our model. It will take N. It will take an instance of Harold. It will take our choice whether to do full or partial, and will take the data frame. Okay, here we go. First thing we add to the model is the choice variable theta c. So the slope of the operating cost. We say it has to be a non-negative number, and we give it a starting value. Same for the replacement cost, it has just to be a positive number. That's the first thing here. Here we choose n numbers that should represent the expected value function. Okay, so that's JuMP language for an array 1 through n called EV, and we will say it has to lie in those bounds. Okay, we just give the solver a little push in the right direction. Okay, we don't want to have crazy values here, so there's no point trying out minus 10,000 here, because we kind of know the problem. We know if you put minus 10,000 into the value function, the replacement probability becomes 0, and all sorts of stuff happens. So you can do these things. Okay, you can bound these reasonable areas, and you should do this by all means. Okay, then if we do full maximum likelihood, we need to go into here. And what do? Well, we get a starting value for those with the same partial MLE function as before. We'll set what is the maximum amount of slots you can go up. Okay. We'll have to create a new variable, which here I called theta last. So the last couple of elements in theta, that's what I mean with this. So basically the transition probabilities. It's a very unfortunate name, but that's what I did. Okay, so theta last, these are just numbers. I'll set a starting value. You can use this function set start value on this vector, and I want to set this to the initial, to these best guesses. You see, so these are the partial MLE estimates. I want to start there. I'll set the last value of this vector to 0 because that's the smallest bin, and I want to impose a constraint that those sum to 1. Okay, so these, that just says these need to be valid probabilities. They need to sum to 1. That's if I want to estimate them. If I do not want to estimate them, I'm here. My J is just whatever Harold thought is the right amount of bins plus 1, and my theta last thing is just the way I created this before. So I'll just have whatever the solver chooses plus an extra element that makes sure it sums to 1. And I return both in this case. In the first case, I only return J, the number of bins. Okay, so one thing you need to know, if you use these objects here, these macros, and you add stuff to a model M, you change the model in place. Okay, so M outside the function will change as a result. So if I go in here, M will have this object stored on it. So that's why I don't have to return anything else here, only J. Okay, good. So then that's the first part. Next, we have to build some parts to basically compute the model solution inside this optimization problem. We'll use what is called expressions. So these are just partial steps, some intermediate results, let's say. Okay, what do? We take the model, we take N, and we take Harold. First thing, we compute the operating cost on each mileage state. Okay, that's just this functional form that we have. That's the state space of Harold, mileage, and that's the structural parameter that we set as a variable up there, theta c. Notice that I tease it out of M with this indexing notation here. Okay, so you can use it like a dict, a JuMP model. So this references the object theta c stored on the JuMP model. Next thing is VK, which is the probability, the value of keeping, okay, the value function of keeping at each state. And I know what this looks like. It's just the operating cost plus beta times the value function, the expected value function. Okay, again, this you see references the object EV that I set as a choice variable up there at a particular mileage state I. The value of replace, you will remember, is just a scalar. Okay, so it's easy. And what is it? Well, it's just this replacement cost. Again, that's a choice variable stored on M. It's the operating cost at the first mileage bin, plus it's the future value at the first mileage bin. Okay, so you remember that was a very nice simplification given to us by the model formulation. Then we compute the difference in those two payoffs. So just replace minus keep at each mileage state. We call that diff v, difference in value at each bin. And from that, we can easily compute the probability to keep again at each state. It's just this, logit form. Okay, and so that basically here, this you would call that the model solution. Okay, so that part here gives the solution to the model given a certain choice of structural parameters RC and theta c, together with a certain shape of the model. EV, remember. So if n, the number of miles is 90, EV in our very simple representation will be a vector length 90, where each entry gives you EV at that state. Okay, it's just a number. And so that then goes here and so on. So that's our representation of the value function, very simple, just point-wise approximation. Okay, next we need to set up the likelihood function, which is the objective function of this thing. Okay, remember? So we're building the blocks to this. So we want to have this. For now, we set up the choice variables and some parts that we need to compute the objective function. Now we compute the objective function. That's called add objective. Okay, so that's a bit longer function, but no fear. So let's quickly go through it. Again, it takes the model. It wants to know whether you do full or partial, and it takes the data frame. It has as a keyword argument the vector of these transition probabilities, which by default is nothing, which we never talked about that, but that's just a standard value for null. So nothing, literally. So it's not a missing value, but it's the computer scientist's null. It's not the data scientist's missing value. Okay, so it's if you have a function that outputs nothing, you make the function output nothing, for example. Okay, anyway, so that's just a stand-in for having nothing, and I can give something else, in which case it's not nothing. Okay, so you can use it like this. So let's see. So we have the data frame. First thing we knew, we need to prepare the data for this, because remember, all right, I need to quickly scroll up. Apologies. So go quickly up to what the likelihood function looks like. We need to compute this thing. To compute this thing, we need TI. Okay, we need to know how many basically rows of data are for each bus I, and then we need to be able to compute that by I, because that's what the likelihood function dictates us to do. So for each I, go through T up to bus I's maximum T. So we need to set up the data like this. If I can just show you quickly the data. That's what the data looks like, but there's nothing that looks like that. Okay, there's no, for example, there's no period here. There's no columns that says period 1, 2, 3, and so on. So we need to add it. Okay, so we add it here. Where is it now? Here. So we group this data frame by ID. We make a grouped data frame. Then we transform it by adding an ID column. No, by adding a time column. Sorry. So I take the group data frame, I take the column ID, and I just add a 1 to length next to that. I call it IT, which is time. Okay, so now I have a second column next to ID. I have 1, 2, 3, 4, 5, 6, 7, 10. If I observe 10 times this particular ID, okay, it's just 10 periods for that bus. Then I count how many rows do I have for each bus. So that's going to give me my TI. And I want to know how many unique buses I have, which is just going to be the number for row of this counter data frame. Then here's the bit that takes care of whether I do partial or full maximum likelihood. If I give nothing here, so if is nothing is true, I want to do full maximum likelihood, so I'll assign to theta last the JuMP object theta last, which are choice variables. Okay, so you need to choose those as well. So those go into the likelihood function. If not, they're nothing, and I don't do anything. Okay. If not is nothing, I don't do anything. Is nothing, I set those values. It's just that was just my way to do this. May not be the best way. Then here's the actual objective function. If you do full maximum likelihood, you have a non-linear objective function, NL objective on model M. You want to maximize that, and here is basically the formula. Okay, so let's try to make some sense of this. So the formula, what is it? It has a first part where we have log of P. Okay, log. What is P? P is the grouped data frame, this guy. For each I, so I need to go over rows of this. And so you see the index I goes from I to big I, which is the number of buses. So I'm going to tease out the data for bus I. I'm going to look at each period, IT in I counter, I and row. You can see that this index here depends on this index. It's going to take this I, that I, you see, this I goes here. Okay, so this is totally amazing. So, oh no, don't go away. This is totally amazing because you can actually write what's written in the likelihood function. The likelihood function says sum over I and then sum over t for period 2 to ti. And so that's exactly the number stored in I counter for bus number I. Okay, so that's really nice, because then I can grab those two indices and I can put them into my data frame. So period IT for bus I, right? The D column is the replacement column. So if that is false, you don't replace. You want to multiply that with the model object probability of keep. At the certain data index of the mileage state. Okay, so that's basically what the model says. This is P at X I. It's that part. That's data. That's data. Real pros would have an iPad here, of course, to write. Next time. And then the next part is if you do replace. So if your replacement array is true, you do 1 minus the probability of keep at the data state. Again, it's the same state here. That's the first part. Then plus the second part, which is just the mileage transition. It's log of these probabilities that you or the solver chose for you again at the data state of the DX1 array. So this, how much do you go up array? Okay, and that's it. So that's this thing. And of course, the cool thing is, as you know, that JuMP will compute a derivative of this for you. So we'll take the gradient of this automatically by automatic differentiation. And therefore, we'll be able to generate very fast code. Okay, so I mean, you can see that later on. I'll do some timings on that. If you do not do full maximum likelihood, you can basically forget about this last part here. And so that's the result. Okay, so it's the same thing without this last part. The objective function just does not take into account that you did choose the transition probabilities. Okay, so this it's a bit involved to do it like this, maybe to understand what's going on, but hopefully you can make some sense out of it if you just look at the likelihood function next to it. Okay, almost there. We need to add the constraints. Okay, and again, the constraints here in this setup are just something that represents what the model looks like, the structure of the model. Again, to remind you, the structure of the model here is encoded in this line. So EV at state xi is just the right-hand side of this. And so when the optimizer chooses, remember, chooses the left-hand side of this. Okay, and he also chooses some inputs for the right-hand side, because on the right-hand side, you have the structural parameters and other things that dictate the shape of the model. The pies, for example, are chosen if you do full maximum likelihood. But basically, the problem here becomes to make those things coincide, of course. Okay, so you know that EV is here, but EV is also part of V. So V is U plus beta times EV, right? So this kind of places a consistency constraint on the whole thing. So whatever you do, you can choose whatever EV you want, but at the end of the day, it needs to be the correct model solution. Okay, so that's what we tell the solver as a constraint. Okay, so in terms of implementation, there's one slight issue, which is if xi is towards the upper bound of the state space of xi, because then you will remember from not here, but from there. Just quickly go back here. Sorry for jumping around a bit. If we are at the upper bound of the state space, you see that there's not all transitions available. Okay, so we have to be a little bit careful in how we index those. So we have to keep good track of this row index here. If we are at this row, we know we have to do something different. Okay, so basically what we'll do, we'll write a constraint. I give this a name, so let's just use the same name. EVCon. Okay, so here, first thing is EVCon. EVCon is going to be applicable for this thing where always we have a full transition available. See, we can always go up 3 steps or J steps. Okay, then there's going to be a region where we can go only up J minus 1 steps here. So we'll have to write a second type of constraints. I'll just call that EVCon 1, EV1, 2 in this region, and then there's going to be a last set 3 where we can, there's no moving up any at all. Okay, so we'll write 3 constraints that will relate to this part here. Okay, so here we are. What do? We have M. Again, we do this business with whether we have to consider theta last as a choice variable or not. Okay, and then we start. So here is the first bit, EVCon, when we can move up any number of states. Guy claims it's easy anyway, whatever. So EVCon is relevant for row indices. Let's just think of this transition matrix. I for 1 through n minus j plus 1. Okay, so that's supposed to be right here. Right here. Okay, it goes all the way up to there, that particular section of the constraint. Okay, so what does it look like? Well, it has to take the object EV out of the model. It has to look at each state I and each of those I's. So suppose the first state, okay, I1. What does it have to do? Well, the right-hand side is just EV, the definition of EV. Here it is. Sum of log, that's the log sum. Log of sum of these 2 discrete choices. And the sum times the probability is just the expected value with respect to the transition probabilities. Okay, so that line here, the J goes over minus transitions. The J goes here. J in the index is how many slots you move up. Here's the J. Okay. Quickly see that somewhere. That's this thing. So it's the integral over x dx, and x is discrete, so that's why it's a sum. Okay, so it's this part. Good. Next section. Need to sum last bins. Not all state progressions are possible. All right, so that concerns the rows. Well, you just have to do some indexing, whatever gymnastics here. It's a bit annoying, but you have to kind of figure out where it starts, where that's. It's not too hard. And then there's basically 2 parts. There's a first part that relates to, well, where you can move up. You know, how many J's you can move up. That's the first part, and then there's a last J that you can move up when you're in the highest state, and that's the probability 1 minus what you had before. Okay, so it's literally that in here. It's literally that number here. Okay, so you have a thing where you don't move up, and then you have 1 minus you don't move up. So all the remaining probabilities summed here. Okay, that's the second, and then the final part, the last row, basically, EVCon n. If you're in the highest state, you don't move anywhere. So the value in the last state is just what it is in the last state. Okay, that's just an assumption on this transition matrix. Very important. So the way he does that is really, that's the key, because that makes it very tractable, and that's very well done. Okay, almost there. So let's see how we can run this thing. Let's put it into a function that we call mpec. Again, some starting values, and let's see what we do. So what do we do? So we create Harold as before at those values. We get his number of states, and we get the data that implies. Then we create this JuMP model, N. Okay? We create it with an IPOpt optimizer. IPOpt we used before, very good open source constraint optimization solver. Okay, if we do full maximum likelihood, we will get out J, and we'll use the add bars function, which we defined above. Okay, so here we created all the variables and added the variables to the model. In this case, we'll add the transition probabilities to the model. If we do not do that, our add bars function will return J and a vector of numbers which represent the given transition probabilities. Okay, so that's going to be a number, a vector of numbers, not a vector of JuMP choice variables. That's the slight difference here. Then we call in order our functions, add expressions. So this was where we set up the model structure, add objective, add constraints. It's exactly like above. And finally, we call JuMP optimize on it, which does all the work. And we return what we want in each case. Okay, try it out. Okay, MPEG at default values runs. That's already good. So fine, that's good. Let's see if we run the nested fixed point at the same default values, what do we get? 7.883, 7.829. Okay, that's very close. 4.65, 4.63. Okay, very close. Okay, so that's I'll celebrate on this note. So that's good. That's close enough. Then let's try to chase some of Rust results. So 90 mileage bins and 0.99. All right, so that's a bit far away. What does the nested fixed point look like at that settings? 8.94, 8.96, 4.25, 4.13. Okay, so okay, good enough. Kind of close those two results. Fine. What if you do full maximum likelihood? So we do the full thing here. We do theta true, do theta true. We get basically exactly the same results in both methods. Okay, here. We get this final bin here. So you see the MPEG thing also estimates the last bin, whereas this one doesn't. The last bin is implied here as 1 minus that. And so that's good. Okay, so we get reasonably close. It's all good. So this is all fine. There's one issue with this particular solution is that if we make in the MPEG function the beta too high, it does not converge. It converges to a wrong solution. Clearly wrong because we can check the numbers. I don't know why that is the case. I have a hunch that it is how I did this mileage transition bin stuff, summing to the last value, etc., etc. Probably not the best way I did it, but so I didn't have much more time to investigate that. You can look at some more results here on a dedicated repo. I set this up some time ago. So there's also timings here. So it's actually a Julia package, so you can just download it and run in your computer. You've got down here, you've got all the results, okay, for certain settings of Rust table. So that's the main thing. It's a dict of all the results, and you can see. So sometimes the full MPEG does not converge to the true solution, depending on the settings here, etc., etc. And so on and so forth. So there seems either there's something wrong or it's just intrinsically that this converges to the wrong solution. I don't know. I did not investigate much further. I think these results are already quite encouraging. I mean, this is really very close. This is quite good. And in terms of timing, it's very fast. Okay, that I didn't show you. I can show you the timing here. So let's just take any one. So this is the nested fixed point, 2.2 seconds. That's the MPEG, it's 0.13. So it's an order of magnitude faster. Okay, so what's the takeaway? So that's kind of the big important moment, not to say anything wrong here. So there's several results from this exercise. First, if you do naive nested fixed point, like I did here, you can probably get faster with MPEG. Okay, just by the nature of using analytic gradients, automated differentiation, and so on, that just gets it much faster. Okay, so if it's hard for your nested fixed point algorithm to write down analytic gradients, if you don't have a structure like Rust's model where this is possible, then MPEG may be a good solution. Okay, you've seen that the way we've done it was not actually too hard to code. like what we've done here with adding, with writing down these expressions, etc. You will always be able to write something like this. Okay, it takes a little bit of practice, but it's not too bad. Okay, and so this EV thing, so the way the model looks, can be very general. So there's no, so here we wrote the expectation like this, just a sum times the probability, etc. But you could do all sorts of things and then automatically differentiate through it, which is very powerful. Yeah, that's it. Okay, but so then, of course, this is not a claim that MPEG is faster than Rust solution, which is wrong, because that's never going to be the case by virtue of the advanced math insights that John Rust uses in order to solve his model much better. Okay, so that's that. Then we run the same thing on a larger state space just to make sure this kind of lines up. So we have 179. So the numbers here slightly change in his estimates. We run the nested fixed point here. Yeah, get kind of okay values. It doesn't get exactly there. Too small beta, I would suggest, and we leave it there. Yeah, I mean, we can try to run it for just for illustration. For 9.9, let's do 9.5. Okay, so I'm not to overburden the whole thing. And here in my console, you'll be able to see each iteration on the solver. So basically, all the time that we wait from one step to the other is a value function iteration. As you see, it's just like, it's painful to look at this. Just goes like, and that's because the beta is so high, so it's going to iterate so many times on the value function. That's it. And as I said, Rust is able to really cut down on this process here, which is good already. So it's going to make it much faster. And also, he has this way to optimize this by writing out the analytic gradient of the likelihood function, which is complicated because it depends on the expected value function. Okay, but again, he has this cool way to differentiate through this with this Fréchet derivative and so on. Okay, so you can, this is running, and at some point it will stop. I'm not sure if we get to see it. It's still kind of some way out, but that's it. So let's just let that run. So here's the data. So that's this main function I copied basically from Bertel's code. So this is very nice, the way they do this, very clean and everything. So have a look at this if you want. And these are all the functions that we needed to solve the model. That's it. Okay, I think that's it. End of this Christmas special. If you have any questions about anything, let's hear. If not, just now you saw how one can do it, so you have a reference, and feel free to grab this code and do stuff with it. It's going to be there for as long as the internet exists, and so free disposal. And that's it. So thanks for joining, everyone. The Bocconi guys know I'm here for the rest of the year. I'm here on the 5th floor. Knock on my door if you want, and I'll be happy to chat and see how things are going. And wish everyone happy Christmas and stay safe. It's going to be another COVID Christmas. But that's it. We'll deal with it, and then it'll be over. Okay. So have a good one. Good to see you guys. All the best. Bye.
Thank you.
Thank you. Bye.
Thank you. Bye.
Merry Christmas.
And you. Bye bye.
Can I ask a last minute question regarding the thing?
Of course.
Can you send us then a kind of template in order to produce the package for the?
Oh yeah, of course. Yeah, good question. I should do that. Oh God, I can't believe I never did that. I'll do that. Okay.
Okay. Yeah.
No problem.
Yeah.
Good.
Thank
All
you.
the best. We'll be in touch on Slack, yeah, for the term project. If you have any issues or stuff, don't hesitate to.
I would.
Yeah. Okay.
Thank you.
Bye bye.
Thank you. Bye.
Bye.